Okay, here is a real tough problem from section 2.4 where it's not already in that nice triangular form where you start off with one equation with only one variable that you can solve and then go backwards from there. So we don't have any way to just get one of the variables by themselves. So we're going to have to do something else. And this is the method called Gaussian reduction that I'm about to describe here. You don't need to know that word, but that's just what that means. It's named after Friedrich Gauss, a famous mathematician from a long time ago. Anyways, the trick is we're going to do stuff to combine three equations with three variables into two equations with two variables. Then we can use the methods from section 2.3 to combine those two equations with two variables into one equation with one variable that you can then solve, and then do back substitution. Let's just go back to just check out, make sure that we understand that's what section 2.3 is about. Here is the notes from that section, which I can't seem to zoom in on. So we had examples of systems of equations like this, where there were two equations with two variables x and y, and here's where we did the elimination method. When you had a negative 2y and a positive 2y, you can add those equations together and you end up with this one equation, 8x equals 40, with just one variable in it that you can solve the normal way. So, but first, in order to do this kind of problem, we have to get our three equations with three variables reduced down to two equations with two variables like that. So we're going to do it the same basic method as before, where we do basically the elimination method. But by the way, the book uses the terminology linear combinations sometimes. That really means the same thing as the elimination method. So wherever you see linear combinations or something like that, they're basically talking about the elimination method. And that's what we're going to do here. So let's see where you can find some variables you might be able to eliminate. I see a z and a z here, which are equal to each other. So maybe I could eliminate z from two equations by multiplying one of these by -1 first. So let's take that last equation, the orange one there, and multiply both sides by -1. Remember, whenever you multiply both sides of an equation by anything, you need to distribute it. So that gives you -3x minus 2y minus z equals -10. And then I'm just going to write the purple one under it again here, so we can see how they'll line up. And then I'm going to add the left sides together, add the right sides together. I'm going to combine the like terms. So the -3x plus 2x is -x. The -2y minus y is -3y. -2z plus z is 0, which was the whole point there, and that gives you a -7 result. Now we want to use two of the other equations, because so far we've used the purple one and the orange one here. There's also the first equation here in green that we can try to combine with one of these other two equations. And the goal is to eliminate the same variable, because we need to have another equation that has x and y in it. So if we eliminate z from maybe a combination of the green one and the purple one, then that will give us another equation with just x and z, and sorry, just x and y. And once you have two equations with those two variables, x and y, you can then use all of the methods from section 2.3, either the substitution method or the elimination method. I think the easiest way to eliminate z here is to multiply both sides of this purple equation by 3 so that you end up with a plus 3z and a minus 3z. Here is what that step looks like. Took the purple equation, multiplied both sides by 3, and when you distribute, you have 6x minus 3y plus 3z equals 9. And I just wrote the first green equation underneath here so that we can see how these will add up. We're going to add the right sides and add the left sides. On the left side, we're going to get a 7x minus y plus 0 equals 5 there. And now we have an equation with x and y and another equation with x and y. We can solve those using elimination now to find either the value of x or the value of y. And there's different ways to do that. One way would be if you're using elimination, I could make this y become a positive 3y, which would cancel out with a negative 3y over here. So to do that, I'm going to multiply both sides of this equation by negative 3, which gives you negative 21x plus 3y equals negative 15, and then you can add both sides of that equation to both sides of the other equation that we had here to cancel out the y's and get an equation with just x in it. This one is going to come out to be negative 22x equals negative 15 minus 7 is negative 22, and when you divide both sides of that by negative 22, you'll get just x equals 1. Now that you have that, we're going to still need to do back substitution to get y and z using the other equations. To do that, we need one equation that has x and one other variable in it. Doesn't matter which one you use. I'm going to use this equation right here. So that means plug in x equals 1 into it. This one's pretty quick to solve. I'll skip the steps here, and you'll get y equals 2. And once you know x and y, you can plug them into any one of the equations that has x and y and z in it. Maybe I'll just use the original orange equation. So that's going to be 3 times x, which is 1, plus 2 times y, which is 2, plus z equals 10. And we can then turn this into 3 times 1 plus 2 times 2 comes out to 7. If you subtract 7 from both sides, you'll get z equals 3. And that should be the solution. X equals 1, y equals 2, and z equals 3. So this is a tricky thing to do, to do all of this elimination stuff where you combine the 3 equations with 3 variables into 2 equations with the same 2 variables, then continue doing more elimination stuff, and it takes a lot of work, as you can see. So just my recommendation for these problems are take your time and try to show your work neatly. The biggest problem is just people making sloppy little mistakes because there's so many little operations you're doing along the way, and if you make a sloppy little mistake once, it'll mess up the whole thing. Now, here's one for you to try. This is tricky, I know, but do your best. You'll feel satisfied when you get done with it because these ones do take a long time. But I just want to do step 1 for you. This is what they mean by clear the fractions from equation 2. You can clear all the fractions by multiplying the whole left side by something that cancels out with the 3's in the denominator, and multiplying it by 3 will do that. So 3 times 2 divided by 3 is 2. 3 times 1/3 is just 1, and 3 times negative z is negative 3z, and then 3 times 1 on the other side is 3. So I did step 1 for you. Try to follow the rest of these steps, do your best, and we'll go over in the next video how to find when one has 0 solutions or an infinite number of solutions, and also how to do a couple application problems in another video. So I'll see you then.